So I promised you I was going to talk about triangulations and hyperplane arrangements and how this connects to sort of the last 2 days of what I've been talking about. Let's just let me just throw a few terms at you and then make sure that we talk about the same thing. So a triangulation is a geometric version of a simplicial complex. So it's so this is a simplicial complex, and by this I mean an actual complex of simplices, nothing abstract. And so since they're actual simplices, that means I don't want to just include the faces of each simplex in my simplicial complex, but I also want to demand that two simplices meet in a face. And so we say we have a triangulation of a polytope if I have a simplicial complex whose support, so the support is just the union of all the simplices, is the polytope. So this is a triangulation. You will hear some other phrases. So let me just mention them. So there's something called a subdivision, and the triangulation is a special subdivision. So there's a relation here. So for a subdivision, I don't demand anymore that I have simplices. So this is just a polytopal complex. Okay, I can just say this, right? So I still want to include every phase of every polytope in my collection here in the complex, and I still want two polytopes to intersect in a common phase. Then sometimes you will hear or read the word dissection. So a dissection is so again, a subdivision is a special dissection. So now I want to I don't care anymore that two polytopes meet in a face. So this is now just a collection of polytopes. Some polytopes P1, whatever, PM, such that P is the union of all of them, and I want the interiors to not overlap. And so finally, if you hear the word cover, now they might overlap. So now I just have a collection of polytopes whatsoever, such that your polytope is the union. What I'll do today is mostly this, but in fact, I do this. So a lot of what I do today, it's really about subdivisions, and in fact, you will see some pictures of subdivisions, even though I think about sort of giving you a flavor of triangulations. Okay, so the first question is, can you always do that? Sort of like this is now, so the question of existence slash construction, right? So so it's a non-trivial question. So give me any polytope in a crazy dimension. Can you always find a triangulation? So can you always find a collection of simplices with nice properties such that the union is your polytope? And the answer is yes. And there is various constructions, and none of them are trivial. So the theorem that every polytope admits a triangulation is a non-trivial theorem. To work for that. So, I really just want to throw some words at you again, and in this case also some pictures. If you're interested and if you want to know more about that, you should look up those words. The nicest type of triangulation is a regular triangulation. Maybe I should regular triangulation or regular subdivision. That's the same thing. So maybe I call this number 1. So this is pictured over here. So, the elevator speech about regular triangulation is as follows. I give you a polytope down here. It's the convex hull of a bunch of points. And maybe one of my points is inside the polytope, like in this case. Then what I'm going to do is I'm going to lift those points, for example, at random heights into 1 dimension higher. So think of these as the original points and lifted to random heights. I guess in my picture they are random positive heights. And then have a magic flashlight that you can beam at your construction here from below, and you make sort of an infinite prism over it. So this is like a sort of a convex hull, this construction. And so if we project this back into the original dimension, this will give you a polytope. I guess I'm projecting not the prism part, but the sort of like the bounded faces of this construction. This has a huge advantage because this has a huge advantage that the triangulation comes from another polyhedron. And so the fact that you have some other polyhedron suggests that there's some polyhedral invariance that somehow you can see in the triangulation, and that's exactly what happens.
Can I ask a question?
Yes, please.
So when you say take the points of the polytope, are you assuming the polytope to be lattice, or if
no.
not, okay, then like who are the points? Like, how do you know that you're just taking 1 point inside that pentagon, for instance? Like, could you have had more of those?
You can have more. We can have more. So what I'm saying is, give me a convex hull description of your polytope, and your convex hull description might be more than the vertices.
Okay.
Yeah,
makes sense.
But you have to give me somehow a description of the polytope. In this case, you give me some description, and I compute the vertices, or you give me actually a convex hull description, and then I use those points. So in some sense, this is not even a construction on a polytope. This is really a construction on a point configuration. And I think then of my polytope as the convex hull of that point configuration.
Thanks.
But unless you asked a good question, because my picture here suggests if you have a lattice, if your polytope is a lattice polytope, and you might have some additional points inside the polytope for your convex hull description that are lattice points, then your triangulation will be a lattice triangulation, right? It will be a triangulation into lattice simplices. Yeah, so this is sort of imply. You know, so whenever somebody like Max or me say the word triangulation, 95% of the time we mean a lattice triangulation. Yeah, so we start with a lattice polytope, and then if we say triangulation of a lattice polytope, well, so if you start with a lattice polytope, we probably mean 99% of the time that we think we want to have a lattice triangulation. Okay, so that's one construction. Construction number two is what's called a pushing triangulation or placing triangulation. So pushing, placing, those are the same thing. So this is what you see down here. So this is a recursive definition. So what I do now is, again, I start with the points, and my end product will be the convex hull of all the points that you see here. And again, you might include points that are that are sort of in the interior or whatever, or the boundary of the convex hull. Yeah? And so now what I do is I start with d+1 points that are affinely independent, make a simplex that we can certainly start out with. Yeah, and then I recursively add a point and recursively construct new simplices. Yeah. And so now the question is like, what does that mean? Yeah, so, and again, I'm only giving you an elevator pitch over here. Yeah, so let's say maybe I'm at step number 4. So I want to, so I got this. Yeah, I got this. I'm at this step of my producing my triangulation, and I want to add vertex number 4. Yeah. So now what I do is I look at the simplicial complex that I have already. Yeah, so this thing down here, consisting, I guess, of 2 triangles and all of their faces. And so now there's a notion of visible facets. Yeah? And it's sort of it's a definition that almost explains itself. So I claim this green facet over here, yeah, of one of my triangles is visible. And so is this green facet, yeah, from V4, from this new point, yeah, and like for example, this facet over here is not correct because I can't see through my triangle. And so you can make this notion precise, and then the 2 new triangles that I'm constructing here are pyramids over those visible facets. So I take, so this new green triangle that I'm constructing over here, yeah, is a pyramid with sort of base my visible facet and then apex V4. And yeah, so actually you keep going, and at the end you have a triangulation. And
there's a question in the chat.
Yes, please.
Oh, sorry. So I think Aryaman was asking for the regular triangulation. Just want to confirm that the map phi is just collecting the lower faces.
the map. Oh boy, I have yeah. I
the
have
capital
notation.
phi.
I have notation here. So phi collects, yes, you could call them lower faces, or in this construction, Ariam, you could just call them the bounded faces, actually. So in this prism construction,
Oh, true.
yeah, so phi collects the bounded faces or the lower faces. And then pi, I guess, is the projection. Thanks. And thanks, Max, for translating the chat.
No problem.
Other questions before the last construction? Yeah, so the last construction is a pulling triangulation. And so you see a picture over here, which is not a triangulation. So that's a subdivision, or if you want, that's a start of a triangulation. Yeah. So what you do over here is you have a polytope, like this cube, this three-dimensional cube, and then you stand at one vertex. So let's say we stand over here, yeah, and you look at all the facets that are sort of that don't contain your vertex. So you can see, so I have, those three back faces that don't contain my vertex. And so now what I'll do is I'll produce pyramids over those facets with apex V. Yeah, so you can see in this case, I produce 3 pyramids. And so this is the start of a triangulation. Yeah, so again, I can sort of do this iteratively. I can then, yeah. So it's sort of like, sort of a little bit of the opposite of number 2. The name suggests that too. Okay, so, but I don't, so for what we're doing, for that matter, what I do, if I need any of this, it's this here, it's this construction. And again, the reason for that is that sometimes I want to make use of information, polyhedral information of this sort of this convex epigraph. This is what this figure up there is called. And I will give you one example of what I mean by this sentence. Really, really, the most important thing that we need for now is that triangulations do exist, and yeah, and then work with that. So I want to give you, I really want to give you an example. And then I'll stop for questions again. So, yeah, this seems like a silly example, but it's turns out to be a very instructive example. So I will show you the what's called the canonical triangulation of the unit cube in d dimensions. Okay, so this is a d-dimensional cube, 0, 1 cube, and I will do something that really seems completely silly, but it turns out this gives you a triangulation. Yeah. So here's what I'm going to do: is I'm going to say, okay, I have all my coordinates are between 0 and 1, correct? And so now I'm gonna order my coordinates. Somebody has to be the smallest, somebody has to be the next smallest, and so on. So I have D numbers, and I order them. And I might as well write them as sort of like indexed by a permutation. So something, pi 1 through pi d. And so if I do this, over, I guess, SD here, then everybody is somewhere, right? Because every point has some, for every point I can put the coordinates in some order. And so I'm allowing equality. So if I have a tiebreaker, then I don't need a tiebreaker. And so now you look at this and you say, well, there's, this is a d-dimensional object with d plus 1 inequality. Whoops, it's a simplex. So this turns out to be triangulation. So can even, maybe we should give this a name, like let's call this, pi, deltas of pi for the permutation. And so you can write down the convex hull description, correct? So, so what are we doing over here? So, if all my, all but the last inequality are equality, right? That's one vertex, I guess, then I have the origin. And if I have equality at the very end and then an inequality before that, I get the unit vector in the pi d direction. And then the next one, I guess I need 2 1s, right? So I have that. And I have a 1 in the pi d minus 1 direction, and so on. So this, the vertices of the simplex, they look like an upper triangular matrix where you shuffled your rows around a little bit. And so this brings me to the other topic that I want to talk about. It's like, so this, I can think of this triangulation. This is induced by a hyperplane arrangement. So a hyperplane arrangement is just a fancy word for a finite set of hyperplanes. Let's call this H. So this is the set of hyperplanes of the form xj equals xk. Correct? So, and I guess here j and k are both between 1 and d. So, if you think about these inequalities up on top, so, well, the first one is maybe not so interesting, but all of these inequalities, there's always an inequality between 2 coordinates, correct? So, so by induced, what I mean, take your unit cube, so here it is, and maybe this is the origin here, so this is the origin, and so now you cut up the unit cube by the hyperplanes of the form, x1 equals x2, x1 equals x3, x1 equals x2 equals x3, and if you're in higher dimension, so on. And this will produce this triangulation. Not every triangulation looks like this, right? So not every triangulation is induced by some hyperplane arrangement. And if I take a polytope and start cutting by hyperplanes, I might not get a triangulation. Yeah? But sometimes, like in this case, the two match. So I know many of you know that this thing has a name. Yes, this is called the real braid arrangement. And yeah, this is maybe in general dimension the first hyperplane arrangement that anybody studies, yeah? Or maybe the second. Okay, I think it's high time for questions. Any comments or questions?
Yeah, what was SD in this? I forgot. Sorry.
Say it again. My notation, you mean?
Yeah.
So that's just a symmetric group on D letters.
Oh, okay.
Yeah. So I look at all possible permutations of my D coordinates. Yeah. And so every permutation gives me one ordering of my coordinates. Yeah. And so this is a union into D factorial simplices. Yeah. So if you look at my picture, you should be able to make out six tetrahedra.
Yeah. Okay. Thanks.
Other questions? Okay, so what is this good for? So number one, this allows you to prove some theorems. Yeah, so I kept saying yesterday, we first triangulate, and then we take the hum over each simplex, and so on. That's number one. Yeah. But maybe more importantly, there's sort of like there's combinatorics here that you can do. So I like to sort of think that there's sort of three points of view. Yeah. So of a triangulation, and so yeah. So now I have to maybe do a little bit of notation. So yeah, triangulation. So let's say sigma 1 through sigma m are like the top dimensional simplices of some polytope P. Yeah, so this notational stuff becomes hard with triangulations because sometimes so like I said, so from this you're going to get an actual simplicial complex, by taking all of these simplices. Let's call it T for triangulation. Yeah, so by taking all simplices delta 1 through delta m and their faces. Yeah. But sometimes, I want to think about I think of these as like full dimensional. So sometimes I want to just think about my triangulation as given by those full dimensional simplices. Yes, this makes sense. In my picture, like I can just think of my my big tetrahedra. But technically speaking, in terms of simplicial complex, this triangle up here is is part of my triangulation. So sometimes I want to think about this, and sometimes I want to forget about it. And so okay, so I want to allow both versions. Yeah. So okay, so number one, is I'm going to write I'm going to write P is sort of like as an inclusion-exclusion union. Yeah. I shouldn't even say is. Yeah? So P is somehow, yeah, so P is an inclusion, exclusion, you know, version. Not even saying what it is, you know, of T. Yeah. So, you know, this becomes important when I want to count, right? So if, you know, so in terms of a triangulation, you can say, okay, P is the union of delta 1 to delta m. Great. Yeah. But now I want to compute the Erhard polynomial of P using the Erhard polynomials of delta 1 through delta m. That's not enough, correct? Because if I want to count, okay, then I count all the points in delta 1, delta 2, and so on. But then I overcounted the points on, you know, where these things meet. Yeah, and so in this version number 1, I really need the whole complex. Yeah. I need to, you know, subtract the points in the intersection and then add the points of the triple intersections and so on. So viewpoint number 2, I can write P as, so now I can actually say what I mean. Yeah, I can write P as the union of the interiors of my simplices. Yeah, so these are now, yeah, so for this I now need again the whole complex, correct? Because if I only would take the interiors of the full dimensional simplices, I'm missing, you know, the stuff on the faces. Yeah? And this becomes a disjoint union, right? So, yeah, so if you think again about counting, this is your friend, correct? So in particular, right? So this in particular, this means, you know, here I can do, you know, I can compute the Erhard polynomial spot on, right? I just, yeah, I don't need to add and subtract. Mm-hmm. But I somehow have to go to the interior. Okay, you know, let's say, hey, that's not bad. Mm-hmm. Viewpoint number 3 yeah, is again a disjoint union, yeah, but yeah, well, maybe I won't say equals, yeah. So I can write this as, yeah, as a disjoint union of half open versions. Half open versions of my top dimensional simplices, delta 1 through delta m. And so what I mean by this, so, you know, let's say I have some polytope and some triangulation, maybe like this, yeah. So, you know, what I'm going to do is I'm going to, you know, so these are my top dimensional simplices, and I don't want to worry about the simplicial complex. So what I'm going to do is I'm going to, you know, I'm going to start somewhere. So let's say I take this, I start over here with my simplex over here, yeah, and then I make my next simplex here adjacent to it, sort of half open here. So I'm going to take away this facet. So that's what I mean by half open version. So maybe the other ones I leave in. So if I'm careful, I can build up my whole triangulation as sort of a disjoint union. And so it turns out there's a construction here that allows you to do this practically, and that construction has again to do with visible facets. Yeah? So I'll see in a moment what's happening in the chat. But so, you know, one practical way to do that, you know, so one example is you construct So in Max's exercise, you will see the notation, you know, HQ of such a delta J. I'll tell you what this means. So what that means is you have, let's say, a triangle like this, and you pick a point Q here. And so, like I said before, there's visible facets and non-visible facets. You know, so the visible facet in this case is this one over here. And again, there's definition. There's a mathematical definition of this. You know? And so, you know, HQ means that you take this visible facet away.
I think in the chat, oh, sorry, are you still working on through the construction?
No. I was just looking at the chat, yeah? But go ahead.
Yeah. Oh, I think in the chat, Aryaman was just asking, how does one decide which edges to leave out? And you're giving one construction.
That's right, yeah. There's other construction, but this is one. Yeah? And
the only one I've ever used.
There you go. So you ask Max about this. They're an expert. You know? So the construction over here, which will not give you the triangulation that I have here, is something like this. You pick a Q somewhere in the middle, yeah, and then you do this construction. Yeah? So I'm picking a Q somewhere in my polytope to make sure that my the facets of my polytope are all there, right? And so now you do that in such a way. So again, so you don't get the picture that I drew in green. Yeah? And you can see, you know, this whatever you're doing here is going to be a disjoint union, because if I look at let's say, you know, a common facet of two simplices, yeah, that's going to be visible for, you know, from Q for one simplex, and it's not going to be visible for the other simplex. So you have to do some work to prove that you get everything, but, you know, that's something you can prove. And Antonia had asked the relative interior of a point, and it's exactly correct. Yes, relative interior of a point is a point, and that's very much something we need here. Yeah. So over here, you know, my triangulation is going to look like, you know, I have some, you know, open stuff here, yeah, and then open stuff here, and then I have open line segments, right? And then in the vertices of the triangulation. And yeah, I very much need that the relative interior of a point is that point. Any questions about these?
I wrote one, so maybe I'm just going to say it.
Please, Alison.
Is this last one, is this third construction giving you a partition of the face lattice, face poset? I'm not sure what it is, because I mean, you're kind of taking, I mean, I'm just thinking that since you're not, since you're so, you're taking a lot of care into not taking the same things twice, I was thinking that that might also say that, say, a certain vertex of the polytope is going to be taken in a certain face of this kind, and a certain edge is going to take only once in another part, and so on.
So that's correct, what you're saying, but I think that's a non-trivial statement, what you're making. Yeah, so yeah, so it's a disjoint union. So what you're saying better be correct. Yeah, every face is exactly in one of the those half-open simplices. I'm pretty sure that's a non-trivial statement. Maybe there's, it's quite likely there's something interesting in what you're saying, but let me tell you my point of view. So I'm interested in number 3 just because it allows me to be as lazy as possible. Correct? I have a disjoint union, yeah, and I only need the full dimensional simplices of my triangulation. There's a price you pay. You have to make them half open in a certain way. Yeah. There's no free lunch. Still, like, you know, if you think about a crazy triangulation and then the simplicial complex that's behind that crazy triangulation, and now you have to compute every single damn Erhard polynomial of every single simplex of in all dimensions of a triangulation. Yeah, I'll do number 3. So that's the main reason to do number 3. And it turns out you can actually do some proofs become easier for number 3 too. So number 3 is both practical in terms of doing computations, and you know, some existing programs, software out there that compute Erhard polynomial do this. They do a half open decomposition. And it's useful to prove some theorems. Also, for the same reason that, you know, you don't have to subtract.
I have a question.
Yes, Arne.
In this example, if you look at the one triangle you have in your drawing there, and you remove one of these edges, then you also have to remove the vertices on each end.
Yes, thank you. Good question. Yeah, so
won't you also remove those other edges as well? At least formally, in a sense. So,
okay, so I won't write it down, but I'll tell you the definition. Okay, so the definition of what I mean by HQ of delta, yeah, is literally you take delta, you take the simplex, set minus all visible facets. Okay, so you remove the whole facet, and therefore, right, all faces of that facet. I think that's what you're referring to.
So then, by what Alessio said, it won't be a partition of these faces because some of them will be sort of removed.
Yes, but there will be then in another simplex in a triangulation. Yeah. So if I think of this as, you know, part of a big triangulation here, I think he was thinking of, the way I understood it, he was talking about the faces of the big polytope.
Okay. Thanks.
Yeah, no, good question. Yeah, these things are subtle. Yeah, so, you know, one has to, yeah, this half open business, what I'm doing here is an operation purely on facets. And that's important, actually. Okay, shall we do our coffee break, 10 minutes? Or, you know, a beer break if you're in, you know, if you're somewhere in Europe already.
Yeah, perhaps we can pause the recording.
Okay, any questions that came up over coffee? Or cats or bunnies or beer? I wanted to show you an example of a half-open decomposition because it connects to some other things. And I just realized maybe Max wants to do an exercise out of this. Okay, so I claim if you place the point Q equals 1, 2, 3, onto D into the unit cube. So I guess we should maybe scale it by something, 2D. Yeah. And see who's visible. Yeah, I claim you make this triangulation disjoint. And by making your simplices half open. Yeah, so so what does that mean in terms of my facet description, right? So I have the same simplices, but I have to now tell you which inequalities are strict. Okay. So this goes a little bit back to Arne's question. Yeah, so by half open, I literally mean taking a facet away. Yeah. And in terms of my half open, my half space description, this literally means I switch some of those inequalities to a strict inequality. So I have to tell you which ones are strict. Yeah, so I have to tell you, so my neighboring inequality is between some x pi j and x pi j plus 1. And I claim what you want here is that J is a descent of the permutation. So a descent is an index of the permutation where numbers go down. So if you write your permutation in one-line notation, a descent is a place where, in your one-line notation, there's a number and the next number following is smaller. And so if you study this permutation statistics in any way, shape, or form, you know the statistics, or you know the set of descents. And then you also know that this gives rise to Eulerian polynomials. And in fact, this is, well, as you know already, Eulerian polynomials, well, at least in the Slack chat, Eulerian polynomials are connected with Erhard polynomials. And so, in some sense, this is how you can see why they appear. Yeah, so the unit cube in D dimensions is, sounds like a pretty important lattice polytope. Yeah, and so if that thing already has Eulerian polynomials show up in some way or form, then they'll probably show up in other ways too, and that's exactly what happened. Okay, so I want to, so I'm not really showing you how to do that, but I wanted to tell you that this is what happens when you apply this construction number 3. And so now I have a confession to make. I said 3 viewpoints, and that's sort of correct, except there's a 4th one. Except there's not a triangulation. Okay. So there's some combinatorial sort of combinatorics, let's just say, it calls for the union of the open simplices, the top dimensional, just the top dimensional simplices, the open ones. Yeah? So, so if this comes from a hyperplane arrangement, then what I'm doing is I'm cutting out the union of the hyperplanes. Yeah, so you can see why this is a fake triangulation. It's not really a triangulation. I'm not writing P as the union of some simplices. I'm leaving something out. Yeah, but I guess I should take the interior of P. yeah, so this appears. And in fact, all of you know an example because I showed you one on Monday when we did graph coloring. So, sorry, this was yesterday, not Monday. Yeah, so this was yesterday when I tried to convince you that the chromatic polynomial is a sum of Erhard polynomials. Yeah, so let's just briefly go through this, right? So what are we doing? So here's the chromatic polynomial of a directed version of a graph, right? And so I wrote this as an Erhard polynomial that comes from, yeah, so this polytope, and lo and behold, it's the interior of a polytope, yeah. And then we said, okay, the chromatic polynomial is the sum of these Erhard polynomials, right? So this really suggests that there is a triangulation behind this, right? So there's somehow, there's some complex, right, of open polytopes. This is not really a triangulation, it's a subdivision. Yeah, there's some sort of disjoint union of open polytopes, yeah, whose sort of Erhard polynomial is, if you add all the Erhard polynomials, gives you this polynomial over here. And in fact, I can tell you where this comes from. So I claim what you want to do is you want to take the unit cube. Sorry, we have to go into the interior of the unit cube. Yeah. And take away what's called the graphic arrangement. Yeah, so every graph comes with a sub-arrangement of the real braid arrangement. And it's the sub-arrangement where I'm only considering the hyperplane xj equals xk for an edge in the graph. So if your graph is a complete graph, you get the real braid arrangement. And so in general, this is a sub-arrangement. This is exactly one of those combinatorial situations where this applies, and I think of this sort of like as a fake subdivision, in this sense what I wrote down. So if you hear the word, if you hear the phrase inside-out polytope, this is what people mean. It's a situation where you have some constraints, some linear constraints that you're interested in, and here are sort of forbidden. So you are sort of given linear constraints, and here are some forbidden values or whatever that you want to take out. Yeah, in my graph coloring case, those are the improper colorings of your graph. I saw there was some stuff in the chat. Let me try to look at it. But are there also other questions about? Max kindly took care of them, as they usually do. Thanks. So I want to now show you something more arithmetic, but let me just go back to the sort of like three and a half viewpoints. So what I like to do with these viewpoints is mix and match. Yeah, so I've used all 4 of them in my research, and it's sort of like, you know, the fun really starts when you look at the same thing sort of, you know, from different points of view. So I encourage you to do that too. Okay, so let's talk about unimodal triangulation. So what does that mean? Yeah, so this means that each simplex is a unimodular simplex. And so again, let me remind you what that means. Yeah, so if your simplex is, you know, it's like in d dimensions, let's say, it's a convex hull of V0 through Vd, then you stand at any of the vertices, let's say V0, yeah, and you look at the differences to the other vertices. Then what you want is you want that this here is a z basis. A z basis of z to the d. Yeah, so these are lattice polytopes of minimal volume, smallest possible. Yeah. And again, you know a unimodal triangulation. Where is it? It's right here. So I claim, so because the simplices over here are convex hulls of, sort of, well, you take the origin and then a unit vector and you keep adding unit vectors. So if you write this as a matrix and you reshuffle that matrix, you see an upper triangular matrix with ones on the diagonal. So that's a unimodular simplex. And so here is, so this standard triangulation of the unit cube is in fact a unimodular triangulation. Okay, so why? Why this is interesting in the Erhard world? So if you have a polytope, so if P has a unimodular triangulation, so then I can write, well, let's just think about it. So it means that each unimodular simplex has a simple Erhard polynomial. So this here has Erhard polynomial, as we discussed yesterday already, in variable n, let's say, n plus d choose d. And we also discussed if I take the interior, I have an n minus 1 choose d. And so this immediately implies, if I take triangulation number 2, if that's unimodular, correct, then a simplex now, right? So remind you myself, So triangulation number 2 is I'm writing my polytope as a disjoint union of relative interior of my all simplices in all dimensions. And so now what happens is, all these Erhard polynomials, they look the same. Well, all Erhard polynomials of simplices of the same dimension look the same. And so, so namely, okay, so if I have dimension j, right, I get the Erhard polynomial. For the interior, I get the Erhard polynomial n minus 1 choose j. and then I have to count how many j-dimensional simplices there are. So, you know, this is part of, this gives rise to the f vector of the triangulation. And so the f vector is the same as when you count faces. So now I'm counting faces in the whole triangulation. And I might need a 1 here. I always forget if I need a 1 here. I might need a, don't quote me, but I might need a 1 here. And so, well, you know, so I think somebody asked me a question about this on Monday. Yeah, so this was also my definition of f star, maybe up to this +1 up front. Yeah, and so, you know, so what you can see now is my f star coefficients. Yeah, so the coefficients for the Erhard. This looks like an Erhard series, the way I defined things yesterday. This is the Erhard polynomial. For the Erhard polynomial, these f star coefficients, if you have binomial triangulation, are just the f vector of the triangulation. And you can prove, okay, you can prove that the h vector of the triangulation appears in the h star vector. So the h star vector is, you know, the h vector of the triangulation. And so yeah, so this is not much harder what I wrote down here. This is really looking at the Erhard series now, yeah, and the fact that you can write the Erhard series over, you can write this as the sum of the Erhard series of the open simplices in your triangulation. And then you massage this a little bit. So you might remember yesterday when I showed you these two theorems by Stanley and by Breuer, and I said H star and H star always non-negative. Yeah, so those theorems, if you have unimatic triangulation, those theorems are they follow from the non-negativity of F and H of the triangulation. And so maybe let me make one more comment over here. Yeah, so so it's kind of like one of those excursions. If you've never seen this, you should be kind of amazed now, right? Because this in particular says that, you know, if you have two different unimodular triangulation of your polytope, it has to have the same H vector. Can happen. You have two very different triangulations. Yeah. At the end of the day, that H vector is the H star vector of the polytope, and the H star vector of the polytope a priori does not know the triangulation. Any questions about this? Okay, so now I showed you a slide of good news. And yeah, I'll show you another slide of even better news. Yeah, so, you know, how could you top? So, you know, you might imagine a polytope with a uniform triangulation is kind of special, and you would be very, very right. Yeah, so, you know, most polytopes don't have a uniform triangulation. Yeah, but there are some polytopes that are even better, namely they have a regular uniform triangulation. You know? So it's exactly the same thing as what we had in the last slide, but this now comes from a regular construction. And so now, then this was the one comment that I wanted to make, you know, about regular triangulations. Yeah, so this now comes from some sort of geometry of another polytope. So your triangulation comes from another polytope, or polyhedron rather, that, you know, has you know, a unimodular simplices on its boundary, or at least on its lower boundary. Yeah, and so that H star behavior really comes from an H vector of, you know, something simplicial. And now, you know, people like, you know, Alessio and Lorenzo, you know, become, you know, wide eyes, because they know now in this situation there's lots of like additional stuff that we know about the H vector. And so this now, you know, after, you know, many pages of work, this gives you some rather strong conditions on H star. Yeah, and so these are here 4 theorems, if you want, yeah, for lattice polytope that admit regular unimodular triangulations. To give you an idea of like how old this stuff is, so these were proved in a paper by Athanasiadis. In 2004, and this was Stapleton about 10 years ago. In 2009, and in fact, Stapleton improved and said this one and this one, you don't need a regular unimodular triangulation. You just need a boundary triangulation. Yeah? So you just need a regular, well, just unimodular boundary triangulation, which is weaker. Anyway, I just wanted to show you these results, you know, in case, you know, so in case you're dealing with polytopes or some collection of polytopes that are special enough that they admit regular unimodular triangulations. Yeah? And for example, if you build something out of unit cubes, that will be the case. Yeah? And so, yeah, that suggests that there's something to be said for chromatic polynomials. And so now you have an idea of this paper that I mentioned on Monday that's not yet published, you know, where this comes from. It comes from this kind of construction. Let me just throw, like, you know, 2 or 3 terms here, because it connects to the other lectures actually. Yeah? These first 2 constraints come from some Cohen-Macaulay properties. You know, so there's a simplicial complex that's actually geometric simplicial complex, and you can prove it's Cohen-Macaulay, and then these things follow. These 2 follow from the upper bound theorem. So upper bound theorem for simplicial polytopes. So there's actually connections to yeah, what you've learned in the other series of lectures. Any questions about this? Okay, so now, okay, so no, like, okay, this looks super nice, right? So if you're lucky enough to have unimodular triangulation, lots of stuff, and, you know, if your unimodular triangulation is regular, or the boundary triangulation is regular, even better, right? So again, this was the good news, but the bad news is these polytopes are super special. And so, yeah, so Ariman asked about the HQ delta. Let's do it, if you don't mind. Let's do that after lecture. Just so I don't have to jump back. You know? But thanks. Yeah, so, okay, you know, this seems not fair, right? So most people I already said, must be late over here. Most polytopes don't come with a unimodular triangulation, but, you know, we know every polytope comes with a triangulation. Okay, so that's, so we know, so P, comes with a triangulation. And we also know triangulation, and also we know that, if I have a lattice polytope, I can make this a lattice triangulation. So my simplices are lattice simplices. And so, so now, the question is like, what if this is not unimodular? Can you salvage something? And the answer is yes. What is this? Unimodular. So this is a really this is a fun story. So this is a result of Beck and McMullen from in 1985, and they proved that you can write the H star polynomial. Not quite as an H polynomial of your triangulation, but something close. Okay, so you can write this as so you have one ingredient for every simplex in your triangulation, and I can write at least the symbols down for each ingredient. So one is the H polynomial of the link. And the other ingredient is what's called a box polynomial. Oops, see. Yeah, so the link of a triangulation is something topological. So what you do is you stand at your simplex and you look at the other simplices in your triangulation that don't contain your simplex, but they're not too far away. And you can make a precise definition, and the topologists in the Zoom room know exactly what I mean. Anyway, this thing has, this is part of your triangulation. So it has some phase numbers and some H numbers, and that's the H polynomial. And this is, so this is topological data. And this is sort of, this is called the box polynomial of the simplex. This is arithmetic data. And in fact, I can define it for you. It's a similar construction as what we did yesterday. So, so what you do is you look at the Hom of delta, so this is a cone over delta. Then this comes with a parallelepiped, fundamental parallelepiped. And then yesterday, out of this, we produced the H polynomial by looking at the integer point transform of your parallelepiped, and we plugged in, just one variable z, and then the rest was 1. Okay. I'm going to do exactly the same thing now, except that I'm going to open up this parallelepiped. So it's another construction. And it's the, if you want, so, here's, here's the topology of your triangulation, and here's the arithmetic. You need both data. Okay, what happens when your triangulation happen to be unimodular? So if if your triangulation is unimodular, that means all simplexes are unimodular. That means that my Hom over H simplex is a super nice cone. The fundamental parallel pipette only contains the origin. And when I make that thing open, I don't have anything anymore. Yeah? So that means everything is gone, except over the triangle. So in here, I have to include the empty face. Yeah? So this needs to include the empty face. And the box polynomial of the empty face in the triangulation by definition is 1. And the topologists in the room know the link of the empty face is just everything. And so you get the H polynomial of the whole triangulation. Yeah, so this generalizes what you saw on 2 pages ago. Yeah, so this gives you actually a way of computing H star. I'm not giving you any details. I'm just throwing a formula at you. But like with much of the other stuff that I showed you, I'm giving you some good things to smell, and then if you're enticed, you look up the details. But yeah, I mean, still, if there are questions, this might be a good time.
Is there a nice combinatorial proof of this formula?
What do you mean by combinatorial proof, Maria?
I don't know, actually.
So in some sense, yeah, so the combinatorics is in those H polynomials. Mm-hmm. So when I say topology, I really mean topological combinatorics, yeah. But in another sense, the box polynomial is really sort of discrete geometry, right? That's okay. You can call it still combinatorics. I wouldn't be mad at you. But yeah, so somewhere you have to count something, which is combinatorics. It also tells, I mean, you can think a little bit about complexity of what you're doing here. Yeah, so you have to understand somehow the topology of your triangulation. Okay, so that means if your triangulation is topologically more complicated, there should be more complicated to compute. That sort of makes sense, yeah. And what else? And so if your simplexes in triangulations are sort of bigger, right? If they they contain more sort of whatever integer points, that should be more complicated too, and that's reflected in those box polynomials. Yeah? Sort of like if the simplexes are sort of fatter, that means that my fundamental parallel pipette will be fatter, right? And then that box polynomial is going to be more complicated. Okay, so yeah, I told you there's a funny story here. So this was sort of a paper in '85, and lots of people knew about it, and lots of people cited it, but people did not really understand what's in there. So it's one of those things that was way ahead of his time. Yeah, and until this is the same Stapleton paper that I mentioned earlier. 2009, Stapleton realized that you can use this for something very pretty. And the green arrow is a philosophical arrow, and the philosophy is sort of what's behind the Dane-Somerville equations. Yeah, so so people who know about Dane-Somerville know that this is some symmetry about H polynomials. And in fact, the links, the H polynomials, the links are also symmetric. And I claim those box polynomials are symmetric sort of almost by definition, because what I did is I opened up this fundamental parallel pipette, so you have some symmetry there. And so Stapleton realized that you can tweak the Beck-Macmillan theorem just a little bit in the following way. So you have a lattice polytope of dimension d. And so now I look at the h star polynomial, and this h star polynomial has a degree, right? So, and in fact, you don't have to compute the h star polynomial to find out the degree. So there's ways to find that, but so the degree is at most d, but it could be smaller. And so let's say the degree is s. And again, you don't need to know h star to know the degree. So this has something to do with existence of interior points in your polytope in the first couple of dilates. And what Stapleton proved is that what you now should do is you should multiply h star by a finite geometric series so that you actually get a degree d polynomial. So if h star has degree s, I have to multiply by a degree d minus s polynomial. Yeah. So take this, multiply by h star. Okay. And so now do a symmetric decomposition. So what I mean by this is I'm going to write this as a sum of two polynomials. And I claim one of them I can multiply by z to the d minus s plus 1. That's not sort of super important. What's important is that I'm going to do this in such a way that these two polynomials are both palindromic. Yeah, so their coefficients are symmetric. It turns out you can always do that. I know if people in the room know this, you can give this to your calculus students. Yeah, so just leave out that z factor in front of b. Yeah, so here's an exercise for tonight. Yeah, give me your favorite polynomial, any polynomial whatsoever. Yeah, you can always write this as a sum of two palindromes. If your polynomial is degree d, then one of those polynomials has degree d, and the other one has some smaller degree. You can always do that. So that's not what Stapleton proved, because your calculus students could prove that. What he proved is that these polynomials have non-negative coefficients. Have coefficients greater than 0. So you might remember from yesterday, so there was the Stanley theorem that says that this polynomial over here has non-negative coefficients. And I'm multiplying by some polynomial with non-negative coefficients. So, you see here a polynomial with non-negative coefficients, and I'm decomposing it. Well, that does not mean that A and B have to have non-negative coefficients, correct? It might be there's some combination, with some positive and some negative coefficients. And so, so Stapleton's theorem is stronger than Stanley's theorem. To say that A and B are non-negative is stronger than saying H star is non-negative. And in fact, out of this, you can, if you then unravel this, you get some inequalities, right? And this is actually straight, out of the theme of my lectures. So you get some inequalities for the H star coefficients. So you just translate what it means that A has non-negative coefficients. That translates into some linear inequalities among the H star coefficients. Any questions about this? I should say philosophy. Yeah. So there's a message here. I have 1 minute. So, and you know, some people in this room have heard me make this message before, but I'm sorry, I'm going to repeat it. I believe people should do this more often, what you see on this page. So not the ensemble thing and not anything fancy, but just this palindromic decomposition. Yeah. So, yeah. So, yeah. So, from very far away, you know, what's my situation? I have some polynomial. Yeah. So let's say it has full degree D. I have some polynomial, and I know, yeah, I know this thing has non-negative coefficients. I believe, yeah, so there's lots of situations combinatorics where this happens, okay? And so here's my charge to all of you. Wherever this happens, yeah, write it like this, okay? So you write it like this, where these are both palindromes. And you want this to have the same degree as H. As you know, your polynomial on the left, and you want this to have a smaller degree. Yeah. So I claim, if you know, so this decomposition, the way I've written it down, is unique. Yeah, and that's the one that you give to your calculus students. Yeah. And so, you know, here's what you should do. I know, try. You know, so like now, so if that's the case, you know, and try to prove that the coefficients of A and B are also non-negative. Because this would give you a stronger statement. Yeah. And of course, you know, I want you to try this in a situation where sort of these polynomials sort of they sort of half present themselves a little bit. Yeah. Yeah. So for example, yeah. So in this case, they present themselves out of this Beck-Mac-Mullen theorem. Mm-hmm. But you know, for example, you know, this project that I mentioned earlier that with these inequalities for the chromatic polynomials, that started out with Emerson, my co-author. He wanted to apply the Stapleton machinery to chromatic polynomials. And you know, you basically know how to do that by now. Yeah? So a chromatic polynomial I can write as a sum of Erhard polynomials. Then I have to worry about this, you know, finite geometric series. So there's some details to work out, but if I can write each Erhard polynomial, H star polynomial as sort of in terms of this palindromic decomposition, you know, there's a chance that I can do that for the chromatic polynomial, and that's exactly what happens. So, yeah. So I encourage you to play with this, okay, in other situations, not just sort of these Polytope stars. Okay, well, thank you for hanging in there with me today, and then maybe, yeah, maybe let's stop the recording, and my brain is open again for questions.